Hello, everyone, and welcome to today's webinar. Thanks for joining. In today's session, we will focus on the intersection of machine learning and physics-based simulation in engineering. We will explore how machine learning can support, enhance, and accelerate simulation workflows, as well as the areas where it is not the right approach. I am pleased to introduce our speaker, Victor Martinez. He has a degree in aeronautical engineering and a postgraduate degree in AI and machine learning. With more than 6 years of experience as a simulation engineer, he has developed structural analysis in Abacus for the automotive, high-tech, and oil and gas industries. Currently, he provides technical support for Abacus users at Bias 3D, helping engineers apply simulation in real-world projects. As Victor presents, I encourage you to submit your questions at any time using the Q&A panel, and we will review them together at the end of the session. With that said, I'll hand it over to you, Victor, to begin the presentation. Thank you.
Okay, so thank you, Manuel, and thank you, everyone, for attending this webinar. So my name is Victor Martinez, and today I will be presenting to you this webinar on machine learning and simulation. So as Manuel said, if you have any questions throughout this webinar, feel free to type them in the Q&A section, and I'll be happy to address them at the end. Yeah, so before we jump into this session, so I wanted to let you know that this is kind of a technical session. So to keep today's session engaging, we have designed this, or most of the slides, in such a way that they are easy to follow. So please bear with us on that. And yeah, so with that being said, I think we can start this webinar. So this is the agenda for today's session. So we'll be covering the fundamentals of both simulation and machine learning. We'll discuss why combining machine learning and simulation, what can machine learning and simulation can do and what they cannot do. We'll present to you this case study that we have prepared for you. Then we'll discuss some challenges, limitations, and some future trends. So now, before starting, so we have different backgrounds attending this webinar. So in order for us, or we wanted to show you the fundamentals of both simulation and machine learning. Basically, in order for us to be on the same page, or try to be on the same page, and hopefully this will make it easier to follow on the case study later in this session. All right, so let's start with what is simulation. And so simulation, if you're not familiar with it, simulation is a representation of a physical system, but in a virtual environment. So there are many ways we can obtain these representations. So what we are seeing in these slides are many representations of simulations, which are animations. But we can also have XY plots, or we can also have tabular representations like in a spreadsheet, or even a final result in our desired units. So simulation is based on using mathematical models that explain the physical system, but using numerical methods to virtualize them, and in order for us to predict how a system is going to behave. So simulation will let us know some what-if scenarios, or it can provide us some insights about how our systems are going to work. And also it let us test or perform tests that we couldn't easily take from physical tests. So now I will present to you the 3 most common types of simulations that are in the industry, or the most common physics simulations that are out there. But I want to present them to you in this format of inputs, calculations, and outputs, because probably most of us, it's something that we are familiar with, because back in school when we were solving math problems, well, most of them consisted on having information, data, or inputs. Then we had to decide the calculations of the equations to solve. And then at the end, we had to get the results, or the outputs in this case. So it's the same format, basically. So let's start with structures. And the technology used to analyze the structural simulations is called the finite element analysis. And the inputs for this type of analysis are the geometry, the material properties, the loads, the boundary conditions, and very importantly, the mesh. And of course, there can be many, or there are many other inputs that we can have in these simulations. Calculations, also we can have many types of calculations in these types of analysis, but these ones are the most basic ones related to the material or the mechanics of materials, and the constitutive relations. And then the outputs. What are the results that we get in this simulation? So most of the time, or the most common ones, are the displacements, the stresses, the strains. If there is some fracture or failure in our components, what is the fatigue life, or if there are any reaction forces happening, and the temperature or any type of heat transfer. So this is about structures. Now, the second type of simulation that we want to present to you today is the fluid dynamics. Mainly the technology is called computational fluid dynamics. And in here, the inputs are the flow domain, the fluid properties, the initial and the boundary conditions, and also a mesh that is in the flow domain. The calculations, so these are the famous Navier-Stokes equations, but we also can have the continuity equations for mass conservation and the energy equation, or if there is turbulence in our models, we can also use turbulence models. And the outputs, we can have velocity and pressure fields. We can visualize the flow over our components. We can get the drag and lift coefficients, and we can have temperature distribution between the fluids and the solids. Now, the third area that we want to show you today is electromagnetics. So in here, the inputs are also the geometry and the material properties, but also we are going to have excitations, which can be the sources, the voltages, the currents. And also, we need to define if we want to, or if we are going to analyze in the frequency or in the time domain. We're going to, or the solver, the tool is going to be solving the famous Maxwell equations. And the types of results that we are getting are the E field and H field distributions, the impedance, inductance, capacitance, some radiation patterns, and also some power losses and the efficiency of our components. So these were some, let's say, some examples of these simulation domains. Now, these are the main benefits that we can see when we are using simulation. So the main, or probably the most popular one, is that by using simulation, we can reduce the cost of physical testing and also the times of this physical testing. We can optimize the designs for weight, strength, and efficiency or cost, or any other type of KPIs that we want to either increase or decrease. We can accelerate the time to market of our components. We can enhance the customer confidence with these validated performance predictions, with these simulations. We can predict potential failures or even test extreme or hazardous conditions safely in these environments because they can be even hard to reproduce physically. And also we can get physical insights from these simulations. So with all these benefits with simulation, what we can easily conclude is that simulation is our friend. And if we have the opportunity, we should be introducing simulation in our workflows. Okay, so that was a brief or a broad overview of how or what is simulation and how it looks like. So now let's now let's move forward with machine learning. So machine learning is this branch of AI that deals with the machine's ability to learn from existing data, and this is very important that we need to have existing data for us to build a machine learning model. And with this, once we build this model, we can use it to perform a certain task or predict a specific outcome based on what it knows. Basically, what we are doing here when we are creating this model, or a machine learning model, we are doing or building a mathematical representation of a real-world scenario. Now, there are many applications of machine learning. Probably most of us, we are familiarized with most of them. So we have, for example, in everyday applications, we have recommendation systems, we have virtual assistants or search engines. In the business and industry areas, we have customer segmentation or fraud detection, mainly for banking systems. We have, in the healthcare industry, we have medical imaging and drug discovery. Now, in engineering, of course, there are many applications, but probably the most common ones are, or the most popular ones are autonomous vehicles, optimizations of processes, and this is something that we'll be seeing in the case study, and climate modeling. And in advanced applications, we can have natural language processing like the chatbots. We can have computer vision like facial recognition and generative AI. And of course, many other examples. So now, in order for us to start understanding how a machine learning model works, we need to categorize, or we need to introduce these two types of classifications of machine learning models. So one of them, or the first classification, is unsupervised learning. So this one is used when we have data or we have many samples and we need to find patterns in this data, in this data set. And then we can group these samples in different groups. And we also have supervised learning. So this one is used mostly to predict. We have regression and classification. So regression is when the target variable is continuous, and classification is used when the target variable is discrete, and we can categorize the samples in our data. Okay, so when we are building a machine learning model, we need to see, or we need to measure how accurate our model is. So, and we can do that before even deploying the model. So one very common practice to do is to split our data set, the data set we are working with. We can split it into data sets. So the first one is called the training data. And this one is used to actually build a mathematical model, to build this model between the independent and the dependent variables. And then the other the split, or the other data set, is called the test data. And this one is used to test the model. So basically, this test data is a set of never before seen values of the independent variables. And we can use them to predict the dependent variable. So once we have these predictions, we can compare the predictions with the real dependent variables and measure how accurate these predictions were. And we have different types of measurements depending on the type of models that we are working with. So for regression models, we can have the mean square error, the mean absolute error, and the R-squared score. So these ones are great to measure our models. The R2 score is used to measure how well the model explains the variance in the data, and we're going to be using it later in this session. And for classification models, we can have these measurements. We can have the accuracy, the precision, the recall, and the F1 score. So these ones, or in here with these measurements, we're going to be dealing with the famous true positives, true negatives, false positives, and false negatives. So this is how we can see this classification, or this measurement of accuracy. Now, we can also have different types of models or architectures of models in machine learning. So we have these traditional simple models like linear regression, we have logistic regression or decision trees. But we can also have more advanced models. So for example, we can have ensembles like random forest or gradient boosting. And these ones can be used to measure or to capture nonlinearities and improve our predictions. And also we can have, let's say, more popular ones like neural networks or deep learning, which are very, very, very famous right now. And also another type of model that we can have is the physics-informed machine learning models. So these ones are used to enforce the governing equations in our models. So we'll see how this looks like later in this webinar. So that was a broad overview of how simulation and machine learning look like. So now let's ask ourselves, so why combining machine learning and simulation? Okay, so simulation, as I was telling you, it is a powerful tool, but there are different problems with simulation. And I'll list 3 problems in this slide for you. So the first one is that when we are running large models, and by large models, I mean they can be nonlinear or very highly nonlinear models. They can involve multiphysics, or they can have a very large number of components. So when we are running them, these simulations can take hours or even days to solve. Also, when we are dealing with simulations with multiple input parameters, we are exploring, or we could be exploring, a very large design space. So we're talking about hundreds or even thousands of possible simulations. And analyzing all of them is impractical. So we can address that later. And also simulations are usually deterministic. So that means that they don't, once we run a simulation, we get the results, but they don't automatically capture the trends, or they don't learn from past runs. So basically what we are saying is that once we run a simulation, they don't remember, or the solver doesn't remember what it has already solved. So every new run starts from scratch. So these are three, let's say, problems with simulation. Now, if we introduce machine learning, we can see how it addresses those issues. So first of all, when we have, or when we train machine learning models with simulation data, we can have faster predictions. So once we train these models, they can predict their results in a shorter time, and we can see that also later. We can also perform optimization studies. So by introducing machine learning, we can explore these large design spaces in a more intelligent way rather than just randomly. And we can also have pattern recognition. So that means that, let's say we start running simulation, and with these results, we start training our models. What we can do with this is that our models will be learning the relationships from previous simulations. And with this information, we can now start running smarter simulations. So basically, machine learning is not replacing the simulation. It is acting as like a shortcut to predict outcomes where running simulations would be too expensive. So to sum up, we can see this as a synergy between them. So when combined simulation and machine learning, so simulation generates high quality data, which is data that is safe, reliable, and physics-based. And machine learning will turn this data into knowledge. So together, these two will enable real-time feedback for engineers and designers. They will reduce the simulation turnaround time. And we can also have smarter optimization and design exploration studies. That is what happens when we combine machine learning and simulation. So now let's address these questions. So what can we do and what we cannot do with machine learning and simulation? So let's start with what they cannot do. So first of all, machine learning cannot replace simulation, or at least not at first. So let's see these two workflows. So at the top, we're seeing a workflow for simulation where we have the inputs, we have the solver that performs the calculations, and then we get the results. And at the bottom, we have the machine learning model where we have the input, we have the model, and then it predicts the results. So at first, it looks like they are the same workflow, but they are not. And the main difference, or we can identify the main difference by asking ourselves, okay, so what are the unknowns in our workflow? So in simulation, the unknowns are the results, which is what the solver is going to calculate. But in machine learning, the unknown is the model that we need to build that can accurately predict the results. Of course, once we have that model, we can do predictions and get the results because they are also unknowns. But the main unknown in our workflow is to get this model. So by this simple difference, we cannot replace simulations with machine learning because these workflows are different. Taking advantage of these same diagrams, machine learning also cannot generate data by itself. So machine learning, or our models, they need data. That data can be either from experiments or from simulations, but we need data. And this data is going to be used to learn. So at the end, machine learning is going to be dependent either on simulation or on data from experiments. These are, let's say, two examples of what they cannot do. Now, let's see what machine learning and simulation can do. So the first thing it can do is we can perform automation and parametric studies. So this means that we can delegate the task of changing the simulation parameters, which can be the meshing or other types of pre-processing or post-processing tasks. Then we can categorize the results and detect trends along these large design spaces. We can also use machine learning for surrogate modeling. Okay, so surrogate modeling, and this is something, or the surrogate models are machine learning models that consist on mathematical approximations of a complex process or computationally expensive process. So that means that we are going to train machine learning models with simulation data in order to replace expensive simulations, and we can get then instant predictions with our models. We can also use machine learning for virtual twins. So a virtual twin is a virtual replica of a physical system, but this physical system or this replica is going to be updated in real time with sensor data. So let's say we are having these simulation results or this data, and we have these inputs in real time. Machine learning model is predicting some outputs, but this machine learning model itself is going to be calibrated with all these simulation data and these sensors data. So this is a brief overview of how virtual twins work. I promise you that there are better or more accurate diagrams of how virtual twins work. But for the purposes of this webinar, this diagram might help understanding them. Now, another thing we can do with machine learning is we can perform parameter optimization studies. So that means that we can start searching high-dimensional design spaces in a more efficient way, and then we can integrate machine learning into these optimization workflows. So let's say we have this example where we have these two parameters, x1 and x2, and we have this constraint defined by this curve. This constraint can be the weight, it can be stresses, displacements, or even the cost of the component. So we can be using, or we can start using a surrogate model and an optimization algorithm to search in this design space. And this way we can easily and quickly identify the most common, or the most optimum design. In this case will be the green point. The red points are these infeasible points because they are not respecting the constraints or the constraint curve. And we can have, or we can use different optimization methods like gradient-based or genetic algorithms. Something else that we can do with machine learning is what is called sensitivity analysis. So traditionally, if we wanted to know the effect of each input parameter on the results, we will have to change one parameter at a time and then study how they are affecting or how this parameter is affecting the outputs. So sensitivity analysis, what they tells us is how much each input parameter is going to affect each output result. And we are going to see that in a, we will be able to quantify them, how much they influence the performance, and we can start detecting some patterns. So we have this example of this aircraft, these geometrical parameters of this aircraft, and we have the lift to drag ratio. So machine learning can reveal how much each of these geometrical parameters affects this ratio. So this is something that it can tell us. It can tell us that the angle attack is explaining 50% of the variance in this lift to drag ratio. We can also get that the wingspan explains 25%, the airfoil thickness to core radio the 15%, and the sweep angle the remaining 5%. So that's something that, this is how sensitivity analysis look like. And finally, another type of study that we can perform using machine learning are non-parametric optimization. So shape and we have these non-parametric optimizations. The most common ones are the shape and the topology optimizations. And in these ones, so we use them when we do not want to change directly the input parameters like the thickness, the length, or the radius of our models. Instead, what we want to do is we want to explore any possible distribution of the material in our design spaces. So our model will be learning the patterns of where the material is either helping or hurting the performance. And then it can use optimization algorithms to find the best topology. All right, so these were some examples of what we can do with machine learning and simulation. Now let's move forward with the case study that we have prepared for you. So when I mentioned at the beginning that we were covering the fundamentals of simulation and machine learning, I wasn't kidding. So this is a beam deflection problem. So this is the most fundamental example that we can do in simulation. Well, most specifically in structural simulations or finite element analysis. So this is a beam deflection analysis. So if you're not familiar with what you are seeing, so this is a structural component that initially is in a horizontal configuration. At the left end, we are seeing it is fixed, and at the right end, we are applying a force to it. So that's it. The only thing that we are doing is seeing how much this beam is being deflected in the vertical direction due to this load. So this has many applications. There are very basic loading scenarios that can be approximated as beams. So for example, we have this airplane where the wing is being deformed due to the lift force of the wing. Or also we can approximate a building as a beam that is under this static wind load. So these are scenarios that of course involve more complex loadings, but we can apply these first approximations as these beams under bending, for these initial validations. So that's how beam deflection looks like. Now I'm going to show you 3 ways of analyzing this type of analysis. So let's start with the analytical solution, and this is very simple. It's called the Timoshenko beam theory. So this is the equation that explains the deflection of the beam. It's very simple. We are seeing this equation with it's telling us, this equation has or takes into account the bending deformation terms and also a shear deformation term. And it's very simple. This is an equation that we can easily input in a spreadsheet. We can get the values in a tabular format, and also we can plot the curve. So this is how it looks like, how this equation is telling us this beam is going to behave under a specific load and a specific material and geometry. So this is the most classic one. Now we also have the finite element analysis solution. And for this one, we need the same information, but more specifically, we need to tell the software what is the geometry, what are the material properties, what is the load and the boundary conditions, and we need to measure it. And this is the second way. This is the technology, or finite element analysis is a technology that has been around for some decades now. And then the third way is using a machine learning model. So in this one, as mentioned before, in order for us to use a machine learning model, we need to train it with data. So in order for this model, what it's going to do is it is going to predict the deformation of a beam in the same way as in a spreadsheet. But now we can ask ourselves, okay, so what data are we going to use to train this machine learning model? And the answer in this case study is that we're going to run many simulations with the finite element analysis. And then we're going to feed our machine learning model with the information or with the results of this simulation. So this case study, this is the workflow that we did or that we followed for this case study. That is divided in 3 steps. So the first one is what we did is we used Abacus, the finite element analysis tool. We use Abacus CAE to perform or to submit a parametric script to populate a data frame that we're going to use to feed the machine learning model. The second step is Python code that we're going to use to train and evaluate different machine learning models and then identify and select the best one. And the third step is using, again, Abacus CAE, but we created a plugin that plots the analytical solution and the machine learning solution. And we'll see how it looks like in the following in some slides. All right, so let's start with the first step in this workflow. So the first one is creating this parametric script. So for that, we need to submit many simulations, and we need information, or we need inputs for that simulations, for those simulations. So the information that we're going to be or to use as inputs in Abacus is called the independent variables. Sorry. So we have these variables. So we have the materials. We're going to be using steel, aluminum, and copper, and of course we are using their mechanical properties. The other independent variables are the geometrical variables, which are the beam length in this range of values. and also the cross-section base and height. So we are using the same value of base with the height. So that means that we are going to have only square cross-sections. And then the load magnitude. So we are going to run many simulations using this range between 1 Newton and Pmax. And Pmax, so Pmax is the calculated maximum loading that each of these beams can withstand before yielding under bending. So this is important because we are telling the model, or we are restraining it to only act in the elastic domain, not in the plastic domain of the beam. So this load is calculated with the material properties and the geometrical properties. So that's why we are only defining it as P max. Then the dependent variable will be the vertical displacement of each of the nodes. So if you're not familiar with the finite element analysis, so what we are seeing here is a beam, and it cannot be seen in here, but it is divided into 10 different elements. And these elements are connected with something called nodes. So what we are going to be using as dependent variables are the vertical displacement of each of these nodes. So these are some results, or we run this simulation or this script running these input parameters. We run it for this study. We created 2,000 samples because we took advantage of the simplicity of this model, because this model had, or each of these samples was solved very quickly. So we were able to populate this data frame in just some hours. So this is how it looks like. Once we populated a spreadsheet or a data frame, these are the results. And we can see these 2,000 samples. And in the columns from B to F, we are seeing the independent variables. So we are seeing what is the material, what are the geometrical parameters, and also the loading, the maximum loading calculated and the loading that was selected. And then from columns G to Q, we are seeing the vertical displacement of each of the nodes. We have 11 nodes because the first one is the one at the left. So in all of the samples, it will be restrained in the vertical direction. So that's the reason why we are seeing a zero displacement in the vertical direction for all of the samples. So this is our data frame. We saved it, or we stored it in a CSV file. And that's the end of this first step. So now the second step involves creating this Python program to train and to evaluate different machine learning models and to select the best one. So we use our data frame that we just generated, but we also use 3 different Python libraries. We use NumPy, we use Pandas, and scikit-learn. So with this, we were able to code a program and evaluate different models and compare them between themselves. So earlier I mentioned you about these accuracy measurements. We have the mean absolute error and the mean squared error, which we want them to be as low as possible. And then we have the R squared, which we want it to be as close to 1 as possible, especially here on the test data. So after running all these models, we identified that the best one was this one, which gave us an R squared score of 0.98. And this is a model, or the architecture of this model is a gradient boosted tree with the use of derived features. So the derived features are some geometrical relations that we derive from mechanics. So these are the derived features that we use, the beam aspect ratio, the beam area, and the beam volume. So we use them because by using them, we are letting the model learn these relationships in an implicit way. Sorry, no, instead of telling our model or letting our model learn these relations implicitly, we are explicitly telling our model that they exist. So this helps our model when measuring its accuracy. All right, so if you're familiar with Python, you may know that you need a Python environment. The most common ones are Jupyter Notebook or Google Colaboratory. But for this case study, what we use Abacus CA because it works as a Python environment if you install the necessary libraries. And it was great because we are using the Abacus kernel to train the model. And it was interesting because this was a kernel that was definitely not developed to train machine learning models, but it's great that we were able to use it. So of course, this is an accelerated video, so it took like 7 minutes to train this model. And this is what we are seeing. Well, in the background, it is being trained. If you're not familiar with Abacus, so this is Abacus CAE, the user interface, and which is used to creating your structural models. And now, once it finished, we can see. Let me just point here. Yeah. So we can see the measurements or the accuracy measurements that I showed you in the previous slide. And at the end, we save this machine learning model in a pickle file. So this allowed us to then use it later in our plugin. So that's the end of this second step. It finishes by having this pickle file with the machine learning model. And then the third step is to develop, or was to develop this plugin inside Abacus CAE. So let me show you how it looks like. So we open this plugin where we have to select it from each of these three materials. We have to input the loading, and then we have to select what is the length and the cross-section base, which, remember, it's the same as the cross-section height. And then once we click apply, it will generate this plot with the calculated analytical solution using these input values. But it will also use the machine learning model to predict the deflection of each of the 11 nodes. So we can see in here different examples where we are changing the material, where we are changing the loading or the geometrical parameters. And it is giving different values in the plot. And we can see that it's not perfectly accurate, but it's giving a very accurate prediction of the beam deflection. So what we are seeing here in this XY plot is our model being validated. And why is that? So the red curve, let's remember, is the analytical solution, and the blue dots are the predicted solution by the machine learning model. And they don't know each other. Basically, they are being just plotted one against the other. And we can see that they are very similar in magnitudes. So they share the same input values, but they don't share the calculations. That's another way of saying it. Now, something else before moving forward that I wanted to show you. As you can see in the plugin, we have the limits, or we are using these sliders to input the geometrical parameters of the beam. And the reason for us to do that is because with the sliders, we can specify a minimum and a maximum value. And let's remember that a machine learning model is trained with a specific range of values. So if we request our model to predict using a value that is outside of these ranges, it's very likely that it will fail. And that's something that is called extrapolation. So yeah, so that was the case study that we have prepared for you in this webinar. And now let's move forward and discuss some challenges and limitations that appear when we are working with machine learning and simulation. So the first one is data quality. So there's this saying, mostly in simulation, that garbage in, garbage out. So that means that if the quality of our input data is bad, then we are going to be having bad results in our simulations, but also our machine learning model will be trained inaccurately, and we're going to get awful results. So the conclusion of this is that our machine learning model will be as accurate as our simulation results. Another challenge, this is something that is introduced when you are learning machine learning, and is the concepts of generalization and extrapolation. So when you're working with unseen data, a machine learning model should predict accurately. And when that happens, that means that the model has generalization. But when the model is memorizing training data and it fails to predict accurately in new cases, it is said that it's overfitting. And on the other hand, when the model misses patterns and on both the test and the training data, it is said that it is underfitting. Now, extrapolation, that's something that we saw in the case study. This is so the machine learning model is trained in a range of values, so it should be performing well within these training these training data ranges. But when conditions change, when you have different input values outside of these ranges, then it's very likely that it will fail predicting accurately. Also, computational cost. So this is something that mess with the surrogate models that, like the one we did in the case study. So the challenge is that training surrogate models often requires hundreds or even probably thousands of simulations. And this might not be practical because sometimes we might have very complex simulations that can take hours or even days to solve. So running hundreds of simulations to train a machine learning model may not be practical. So it is very understandable that surrogate models cannot be used for every application or every scenario. And also another challenge is the integration into engineering workflows. So there are some technical barriers. Sometimes the tools or the machine learning tools cannot be integrated easily into our workflows, but also within the teams. For example, we can have analyst teams that can struggle with the machine learning or with some Python pipelines. But also on the other hand, we can have machine learning experts that don't understand simulation constraints or simulation details that are in our analysis. So of course there are other types of challenges and limitations. These ones were just a few. Now let's review some future trends, and I would say not only future trends, these are things that are happening also in the present. So physics-informed machine learning. So this is something that I briefly mentioned earlier. So these are machine learning models that have embedded physical laws, like the conservation of energy for fluid dynamics. And this is used when we want to constrain our models to physical laws. So basically, the physical laws of the system that we are analyzing, we can insert them into our models. And also, we can tell our models the important physics features to follow or to obey. Now, this is great because when we introduce these physical laws, we can reduce the need for large data, and also it can allow us to extrapolate to untrained ranges. So that means we can extrapolate to samples outside our training ranges. Another trend is the democratization of machine learning in CA tools. So machine learning is being introduced to simulation platforms. So this has a great impact because, for example, if an analyst runs hundreds of simulations in order to train surrogate models, they can use these or they can share these models to designers or to other engineers that they can easily or quickly validate their designs early in the design phase. So that's great, and the engineers can have access to these machine learning workflows without being machine learning experts. So the trend is to insert this type of technologies in the most easier way with just one click. For example, one-click surrogate model generation, or running a parametric study, or performing a sensitivity analysis in these CAE tools. And another trend, and we'll use this trend to wrap up this section, is to introduce or to use autonomous engineering workflows. So we can start having these end-to-end pipelines where machine learning is automating the pre-processing, it is running the simulation, it is analyzing the results, and then it can suggest the next steps. So basically, what we are doing is we are bundling this and then delegating it to an autonomous system. So of course, this requires a lot of settings that the users need to set up. But it's important to keep the engineers still supervising and monitoring these workflows, but they can also start focusing more on the decision making of their simulations. All right, so that was the presentation. That was the webinar. This was the webinar that we have prepared for you. And I want to close by emphasizing that the fusion or the combination of machine learning and simulation isn't really about replacing the simulation. It's mostly about start asking ourselves, so what is the best design that we can have across thousands of possibilities, and then getting the answer in a short period of time. So that was this webinar that we had prepared for you. And yeah, so if you have any questions, I'll be very happy to address them.
I think that's it for today. On behalf of Bias 3D, thank you all for joining us today. And thank you, Victor, for this great presentation and sharing your knowledge. Yeah, so we hope to see you again in future webinars.